Okay, so can you see my PowerPoint window?
Yep.
Good. Okay. So today I'm going to give you a recap of what we have seen so far in this module. So this recap will cover 3 questions out of 4. So 75% of the question marks will be covered here. And one thing you have to keep in mind is that in the exam, you will see most of the questions are descriptive. So like you have to explain, let's say how a series regulator operates or how a shunt regulator operates and things like that. So in this kind of descriptions, or try to be, try to be a bit innovative. Okay, if you just copy paste what is in the slide, okay, then that would be reflected on the mark as well. Okay, so try to give your own understanding, so how you understand the circuit operates and things like that. Try to connect it with real life where you can see this kind of application and things like that. Okay. So the first topic that we are going to cover is that I'm going to cover today is the linear voltage regulator. So this is actually the topic that we started the module with. So linear voltage regulator, what is the linear voltage regulator? It's actually a simple circuit. Second, please. It's actually a simple circuit that that can ensure constant voltage across your load. And it is not a switching circuit, means there is no switching element, so you do not turn it on or off, something like that. But here you have some sort of like passive element base, so it could be either resistor, it could be like a Zener diode or transistor, something like that. Okay, so all these passive elements we use here to regulate the voltage at the load side. So voltage regulator is a device which maintains the output voltage of an ordinary supply constant irrespective of load variation and AC input changes. So even if there is a change in the input here, AC or DC, it will ensure that your load, the voltage across your load, which is V out, is always constant. Now, in general, these kind of regulators are 2 types. So type 1 is a series regulator. So where, as you can see, the regulating element is in series with the load, and because here we see that it is in series. Okay. So the input series connection to the load. And then in the shunt regulator type, our linear voltage regulator is actually in parallel with the load. So before going into the details of the linear voltage regulator, let's have a look at a Zener diode voltage regulator, because most of the linear voltage regulator, not most, almost all of them, uses a Zener diode voltage regulator. I'm talking about the simple one. The other one, the commercial programmable one, they may have some different topology. So what is the difference between diode and Zener diode? So this is the diagram of our diode. So as you can see, this is the positive terminal, this is the negative terminal. In the case of Zener diode, the ending terminal has like this kind of Z shape. Okay. So they have their operation principle is slightly different. So regular PN junction diode, you use it to operate in the forward bias region. Okay. So in the reverse bias case, what a regular PN junction will do, it will actually block the flow of current. So if you bias it with positive voltage, it will let the current to pass. But if you bias it with negative voltage, it will not let the current to pass. Now, of course, there is a limit to its voltage, which is called the breakdown voltage. When the device reach that voltage, then there will be a breakdown of your device and your device will be gone. Unlike normal Zener diode, unlike normal PN junction diode, Zener diode also behave as a normal diode, but it is actually designed to operate in the reverse biased region. So in the reverse biased region, conduct current at a fixed voltage under certain conditions. So when you put it in a reverse biased situation, its voltage will be roughly constant. Okay. And this constant voltage will actually ensure that the voltage across our load is constant, because we know that the voltage across two branch is in two parallel branch is actually constant. So if you have a Zener diode fixed voltage here, so this voltage will be reflected on your load side also. Now, how Zener diode voltage regulator works? So let's say we consider the case where V in is greater than Vz. Okay. In this case, Zener diode works in the breakdown region. Breakdown region means it's in the reverse bias mode and maintains constant voltage across the load. Since your input voltage is greater than the Zener voltage, so this Zener voltage will be constant and this constant voltage will be supplied to the load. Now input current, to limit the input current, we use a series resistor, RS. So this is the basic operation. Now, how actually this operates, like this is the what I presented to you just now is the overview. Now let's go into the details. So we can consider the case 1. In case 1, our input voltage is higher than the nominal value. So let's say our nominal value is 20 volt. Now suddenly my input voltage become 22 volt. So V in is actually greater than the V in nominal. Okay. Since the output voltage is constant, now what is happening? Since V in is actually greater than Vz, so what will happen? This Zener diode voltage will be constant. Since the output voltage is constant, then VRS, we know that if we apply Kirchhoff voltage law in this circuit, what we have? V in equal VRS plus V out. Okay, this voltage. So since the output voltage is constant, so VRS would be equal V in minus V out, means there will be more drop across this part of the circuit. So since you have more drop in the circuit, this will ensure you have constant voltage across the load. What if your input voltage is at nominal value, but your load resistor value actually decreased? In this case also Zener diode operate at the Vz, which is the Zener voltage. But if we apply this formula, so VRS equal what? V in minus V out. Okay. Then we know that V equal IR. Okay. Now what is I? This I, if we apply Kirchhoff's current law here, I equal IL plus IZ. Okay. Then just by substituting this, we can see that the excess load current will come by a reduction in the Zener current. So since you have more load current passing through this will cause a reduction in the Zener current, and that's how it will ensure constant voltage across the load. Now we have seen the operation of our circuit when the input voltage is greater than the nominal input voltage, when the load resistor reduces and things like that. But one thing we have to keep in mind that this Zener diode, to operate it, we need to ensure there is a minimum current, okay, flowing through this Zener diode. If that minimum current does not flow through that Zener diode, this Zener diode will not be activated. Okay. Now, if we keep, as we can see previously, that if the load resistor decreases, then there will be a reduction in Zener current to maintain constant voltage at the load side. Now, if the load resistor value keep decreasing, Zener current will also keep decreasing. By keep decreasing, there will be a moment, okay, where our Zener current is actually less than the minimum Zener current that will keep the device active. So we need to find the minimum load resistor value that will ensure that the circuit is operating. Okay. So this one is actually quite simple. If we apply voltage divider rule here, we can find this equation. Okay. For the RL max and for the RL min here. You see. So we can find the minimum and maximum value of the resistor that will ensure that our circuit is operating. Okay. If the resistor value is outside of this limit, then what will happen? It will not be activating the circuit, and as such the voltage regulator will not be operating. Now, Zener Diode voltage regulator, although it is simple to implement and operate, but it has some limitations. So what are the limitations? So first limitation, it is low efficiency for heavy load current. So think it like this way, I equal IL plus IZ. Now, if you increase the load value, what will happen? Your IL will increase. IL will increase means that your overall current is also increases. So high current means there is a huge resistive loss here, because we know P equal what? I square R. So we will have a huge amount of loss in this part of the circuit. So this circuit has low efficiency. Okay. Moreover, practical Zener diode, although we say that Zener diode's voltage is constant, in practice it is not true, because Zener diode is not an ideal device. So it has its own impedance or internal resistance. So instead of V out equal Vz, it's actually V out equal Vz plus Iz Zz. So this is the internal impedance of our Zener diode. Now what will happen if there is a large variation in IL? This will also cause a large variation in Zener current. So when there is large variation in Zener current, what will happen? Your output voltage will also have large variation. Now, when we use a linear voltage regulator, we do not want it to have large variation. So this kind of circuit is suitable when BEng and RL do not vary much. Okay. If there is large variation, then this kind of circuit is not suitable. Now we need to ensure that to ensure the proper operation of Zener diode means the circuit will be always on. One thing we have to ensure is our RL min and RL max is maintained, means our load resistor value is always within the limit. So always within the min and max. Okay. So the Zener diode must work between Iz min and Iz max. So previously I mentioned that there is a minimum current that will ensure that the Zener diode is on. But there is also a maximum current that will ensure that the Zener diode is operating properly, in the sense that if you keep increasing the current, you know P equal I square R. Okay. Or you can also replace it by the impedance. Now, what is happening is this loss will generate heat. Okay, whenever current passes through some element, you can feel that the element is getting heated. So now, if you keep increasing the Zener current, then what will happen? The heat across your Zener diode will also continue to increase, and at some point, this will burn your device. Okay, so there is a safe operating current even for the Zener diode. So your Zener diode also need to operate between Iz min and Iz max. So Iz min will ensure that the circuit is on, and Iz max will ensure that the circuit is healthy. Okay. So the Zener diode should not be allowed to dissipate more than the Pz max. Okay, this is the maximum power that your Zener diode can dissipate before harming the device. And finally, the load resistance should not fall between RL min. If it falls between RL min, then your Zener diode will turn to off state. Off state means your circuit is not operating. Now, Zener diode voltage regulator is simple, but it does not have a feedback mechanism integrated into it. So we can use transistor to integrate feedback mechanism. So what is feedback mechanism? It's like a control. So you compare something with a reference and you calculate the actual value. From that you get the error, and that error you pass through a controller to get your desired output. In your coursework, you have to implement feedback controller for buck boost converter, isn't it? So transistor can be used as an indirect or direct controller as well. So what is transistor? Let's give a quick recap. So a transistor consists of two PN junctions formed by sandwiching either P-type or N-type semiconductors. So here in the PNP semiconductor, we have two P-type semiconductors sandwiched by one N-type. or in the NPN case, the most popular one, two N-type semiconductors are sandwiched by a P-type semiconductor. Now, transistor has three sections: emitter, base, and collector. So, emitter is always forward biased, okay, and our collector is reverse biased, okay. So, why this is the case? Because when this part is forward biased, then the majority carrier will be pushed from this part to here. And here we have minority carrier. So in this case, this is electron. In this case, here the majority carrier is hole. Okay. And here the majority carrier is electron. So electron and hole will combine, and that will give rise to a base current, and the remaining will go to the collector. That will give rise to the collector current. Okay. So here the operation is clearly explained, and what the thing that you need to know is this equation. It's IE equal IB plus IC. Okay. So emitter current equal base current plus collector current. Okay. How a transistor series voltage regulator operates. Previously our Zener Diode voltage regulator was something like this. We have a series resistor, then we have a Zener Diode, okay, and then we have a load, okay. Now what is happening? In addition to the Zener Diode and the series resistor, we also have a transistor that is in series with the load. And as you can see now, the series resistor RS has a different configuration. Okay, so how this one actually operates? So the base voltage of Q1. Okay, this is the transistor, and transistor is a three-terminal device. So this is the base, this is the emitter, and this is the collector. Okay. So the base voltage of Q1 is held to a relatively constant voltage across the Zener diode. Thanks to the Zener diode, the base voltage across the Zener diode is quite constant. And here, by applying Kirchhoff's voltage law, we can find that V out equal Vz minus Vb. Now, if for some reason V out decreases, then the increased base emitter voltage, if this one decreases, this one will increase. The increased base emitter voltage will cause Q1, so the transistor, to conduct more. If the transistor conduct more, it means more current will flow. More current flow means our output voltage will increase. Similarly, if for some reason the output voltage increases, then what will happen? That the base emitter voltage will decreases. This will cause the transistor Q1 to conduct less, and this will ensure that the output voltage return back to its nominal value. Okay, so what is the advantage of this circuit is that changes in Zener current reduces by a factor of beta. Because of the transistor, now less current will flow through the Zener current. It means we will have less variation in the output voltage, less drop in the Zener diode, and things like that. However, it has some limitations. First of all, output is not absolutely constant, as both the base emitter voltage and Zener voltage, they changes with respect to temperature. So if you increase the temperature or decrease the temperature, there will be a change in the output voltage, because these are semiconductor devices and they have a dependency on the temperature. And this circuit is not easily controllable because we do not have any direct feedback. So to overcome the limitation of transistor series voltage regulator, researchers came up with a new idea, which is called transistor series feedback voltage regulator. So here, this is the original transistor feedback voltage regulator, series voltage regulator, and now we add this additional part to provide feedback. And so how this circuit operates, this uses a principle of negative feedback to hold the output voltage constant despite changes in the line current and or load resistance. Okay, so the Q2, this is the pass transistor because the current will pass through this to the load. Voltage divider So here we have R1 and R2. This is actually voltage divider. This will provide the negative feedback voltage to the base of Q1. So this Q1 is actually your controller, and the voltage divider circuit here will provide the necessary feedback voltage to this controller. And the feedback voltage VF will actually control the current through Q1. And this current through Q1 will control the current through Q2, and this will ultimately control the current that is being sent to the load. Okay. So suppose our output voltage is actually greater than the reference voltage. So if output voltage is greater than the reference voltage, then what will happen? This feedback voltage, so the voltage divider rule wise, this voltage will also increase. And this increased voltage means there is more voltage, high voltage to your base of transistor Q1. And higher base voltage means more current will flow through the collector of Q1. And since this current, most of it will flow through R3, then a small amount of the current will pass through Q2, means my output voltage will be stabilized. In the case when output voltage is actually less than the reference voltage, okay, then this feedback voltage will decrease. This will cause less current to pass. Less current passing through Q1 means more current passing through Q2, and this will ensure that our output voltage increase to the reference value. So here you can see some mathematical derivation, so how it actually operates. So voltage divider R1, R2, this part actually provides something called the feedback voltage. And if you apply Kirchhoff's voltage law, so we want to find the voltage across this, so R2 by R1 plus R2, this is the overall resistor. Then if we apply Kirchhoff's voltage law, we find VF equal VZ plus VBE. So after simplifying, we get our output voltage is actually a function of this. So just by controlling the VBE, so base to emitter voltage, we can actually control the output voltage. And this base to emitter voltage will actually be controlled thanks to this feedback, this voltage divider feedback. So what we have seen so far is actually called a transistor series voltage regulator. Now we are going to see another topology, which is transistor shunt voltage regulator. So here the transistor is actually in parallel to our load. So the transistor Q1 is in parallel with the load. By shunting the current through Q1, this transistor, the load voltage is controlled. So if you, pass more current through it, or less current through it, that will have an impact on the output voltage. So the voltage drop across RS, which is the series resistor, depends on IRL, actually the load current. And we know this formula from previous calculation is V out. So output voltage is actually Zener voltage plus base emitter voltage. Okay. Now if for some reason RL decreases, so there is a change in the load, this will cause the base current to decrease. As a result, collector current will decrease, and this will actually increase the IL, load current. Okay, or the vice versa. So if for some reason RL increases, then IB will increase, and this will cause IC to decrease, because if you remember, I equal IB plus IC. Okay, now similar to other topology, this one also got some limitation. Firstly, large current will pass through RS, means series resistor. So all the current will actually pass through RS. So if you are operating it at a heavy load condition, this circuit will have low efficiency. And this circuit may also have potentially over voltage condition. Okay. Now we have a simple math to solve. Okay. Please carefully try to understand it. Okay. So in this circuit, what we have to do, we have to find the output voltage, the load current, source current, and collector current. Okay. So output voltage, we already know the formula V output equal Vz plus Vbe. Okay. Now, what is Vz? 8.3 volt. Okay. And what is Vbe? If no value is given, you can always assume 0.7 volt. So you got 9 volt. Clear? So this one is solved. Now we know that the current through our load. So current through the load, this one, V equal IR. So I equal V over R. Here it is V out over RL. So what is V out? V out is 9 volt. And what is RL? 100 ohm. So you can calculate it. So 9 over 100 volt, 9 volt over 100 ohm would be 0.09 ampere. Okay, now in this circuit, if I apply Kirchhoff's voltage law, what I get? I get V in is equal V out plus VRS, or VRS equal V in minus V out. Now we know that VRS equal IS RS equal V in minus V out, or IS equal V in minus V out over RS. Okay. So our V in is actually 22 volt, our V out is 9 volt, our RS is 130 ohm. You can find the value. And finally, we have to find the capacitor current. Actually, if you apply Kirchhoff's current law, what we get? We actually get IC equal, so this current is equal this current minus this current. So IS minus IL. So you already found the IS here. You already know the IL here. Then you will be able to find the value of capacitor current. Okay. So in the exam, if I ask you that explain the operation of, let's say, transistor shunt voltage regulator, will you be able to do that?
Probably not.
Probably not. Yeah, why not? You have the operation here.
You just need practice at it. Like, I know that you go through it, but the only way that, or personally, the only way that I learn is by doing it over and over again. And I won't be able to learn it by just doing one example. I'll need practice questions, which would be useful if you could give us.
No, the question is, let's say the question is, explain the transistor voltage regulator. So, like, this is the operation. This is what you have to explain.
Okay, yeah. Well,
okay.
Have a go at it.
Yeah. So in this, so if this is the question, so what would be your approach to answer it? So first of all, you have to give the circuit diagram. Okay. Then you have to explain the operation. Okay. So what happens when the voltage increases or voltage decreases, or the load resistor value increases or decreases, and things like that. Then you have to mention some limitations, and also you have to give some potential application. Okay. Then, like this kind of circuit, if I ask you like how a transistor series feedback voltage regulator works, okay, then again you have to give the circuit diagram and you have to explain the operation and things like that. Okay. And the math would be something similar like this. Okay, so if you understand this math well, you will be able to answer the exam question. Don't worry.
When you say give the circuit diagram, so will we have to draw it, or is it's already going to be in the exam, like given?
No, you have to draw it.
Okay.
So can I just check with this Digi exam software? Do we have to write out the answers to the exam and then scan them up and upload them?
In the DigiBook exam, you mean?
Yeah.
Unfortunately, I do not know how it operates. Okay, I can check, but I think it should be like that. Okay, maybe it's just a way of monitoring students. Okay, so if you are doing something that is not allowed, but yeah, I think it should be something like that.
If we're doing it by hand, then it should be alright. But if we have to do it on the actual digital thing, then it'll be a problem.
You don't have to use any software. Okay, so a rough diagram would be okay. Okay.
Don't you need your phone to take pictures
Sorry.
of it? Don't you need your phone to take pictures of it to send it through?
Pictures of it.
Yeah, you need to take pictures of the work you've done during the exam. Isn't that how it works?
Yeah, we'll need to use our phones to scan it in, but in the Digi exam it says you're not allowed to use your phone. So it's sort of a bit contradicting itself there.
And the thing is, if you copy this, like you have to draw this picture. If this question comes in the exam, you have to draw this picture on your own.
It's not with just this question in general. If we're writing it out on paper and scanning it in, none of us have scanners at home, so we have to take photos of it and scan it in that way using Adobe Scan. But Digi exam says it monitors if you use your phone, so it'll flag up that we're failing even though we're just doing what's required for the exam.
Okay. So how will you be able to write things in Digi exam? It's like through typing, or
we don't know. We've never used it before. We're hoping that you could tell us that.
I also never used it before.
Well,
I'm in the same situation.
Why are we using it then?
Yeah, it seems a bit backwards to be first time using it if none of us have used it or had any practice, and we only get told about it a month before the exam.
Yeah, to be honest, I have no idea why BCU administration took this decision. I think this time they could have arranged, like a regular exam, because now everything is open. So anyhow, so we have seen already one thing, which is the transistor, which is a linear voltage regulator, and in addition to what I have shown, there may be something related to voltage regulation. So what is actually voltage regulation and things like that. Okay, so please have a look at that. So this is roughly like one question that's in the exam. Now let's go to the next question. So in the next question, this would be about the DC to DC converters. So we are going to see buck converter today. So what is actually a buck converter? Buck converter's objective is to reduce the DC voltage. So if you have, let's say, 10 volt and you want a 5 volt output, then you will use a buck converter. But if you have 10 volt input but you want 20 volt output, then you have to use a boost converter. And if you have a dual objective operation, so you want either 10 volt or 20 volt depending on the user choice, then you have to, either 5 volt or 20 volt, then you have to use something like buck boost converter. So DC to DC buck converter is actually the DC equivalent of an AC transformer. So the power at the input side and the output side are same. Okay. Although when we say that input and output power are same, we are assuming that there is no loss in the circuit, which is not true. But roughly the input and output power will be same. So in practice, in theory, the ideal focus is lossless objective, means our input power equal output power, which means that V in I in equal V out I out. And from this, we can find this relationship. So as you can see, if your output power, if your output voltage decreases, it will cause your output current to increase and vice versa. So before going into the operation of a complicated DC-DC converter, let's see a simple inefficient DC-DC converter. This is actually nothing but a voltage divider. So if we apply a voltage divider, we have this formula, and from this formula we can find the voltage conversion So R2 over R1 plus R2. Now this circuit can ensure that you have desirable voltage at the load side, but if there is a change in the input voltage or there is a change in the resistor value, this circuit will no longer be operating at the correct voltage. Moreover, you will have huge loss into this resistor R1. Okay, so if your input voltage is 39 volt and your output voltage is 13 volt, you can see that the efficiency of your circuit is only 33%. So it is unacceptable except in very low power applications where you don't care much about the efficiency. Now, another method of lossless conversion is actually by using averaging. So let's say I have a switch. Okay. Now this switch, when it is closed, the output voltage is 39 volt, and when the switch is off, the output voltage is 0 volt. So by applying a periodic opening or closing of the switch, I can ensure. So let's say I open the circuit for 33% of the time. So 39 volt times 0.33. Okay. Would be roughly 13 volt, and then I keep the circuit off for the remaining 67% of the time. Okay, and the average is actually 13 volt. Okay, now the problem of this is, although the average is 13 volt, but 2/3 of the time my circuit is actually off. So if you have a, let's say, audio system that's on for 33% of the time every cycle, so the music you will hear is actually not going to be a good experience. So you have like in the lyrics, like in one word, you can hear one character, then two characters off, then again another character, and things like that. So this is not ideal. So although here we have lossless conversion, but this is not acceptable. So this actually gives rise to the idea of DC-DC converter. So what if, to make sure that there is always some voltage across the stereo, we just put a capacitor, because you know capacitor can hold the voltage. So if we add a large capacitor in parallel with the load to control the ripple, then what will happen when the switch closes? Let's say it's like this. The source current spikes to a huge value and burns out the switch. It means there will be a huge current flow through this circuit, and this current flow will actually cause the switch to burn. Okay. Why huge current will flow? Because you know, when the switch is closed, this branch is parallel to this branch, and you know, in parallel voltage remains constant. So what will happen, since this voltage is not 39 volt, then there will be a huge current flow to make sure that the capacitor voltage is also 39 volt, and this huge current flow will burn your switch. Now try adding an inductor to prevent the huge current spike. Okay, if you put an inductor, but now if the L has current, let's say your inductor also got current, this inductor current will do what? When the switch will try to turn off, this inductor current will cause again high di by dt. Okay, so high ratio of change of current, and this will also burn your switch. Okay, so the solution to this problem is just add a diode. So this diode, thanks to this diode, whenever even though there is current in the inductor but the switch will try to open, there is a path for the inductor current to flow instead of burning the switch. And this is actually the topology of a DC-DC buck converter. And ideally speaking, this is a lossless conversion, but in practice, you know, your switch is not ideal, your inductor is not ideal, your diode is not ideal, capacitor is not ideal. So there will be losses in all of these elements. But this circuit has relatively high efficiency compared to the circuits that we have seen before. So to understand the operation of DC-DC back converter, let's say in the exam there is a question that explain the operation of DC-DC back converter. So you can start with this story, like how to make a DC-DC back converter. So you can start with this lossless DC-DC conversion and then show individually if we add a capacitor, what will happen. If we add an inductor, what will happen. If we add a diode, what will happen, and things like that. Then you can also provide some diagrams, so like the voltage and current waveforms and things like that. And as I have shown you previously that to understand the DC-DC converter, you have to understand the fundamental voltage of across capacitor. So the capacitor, the current through a capacitor, you can represent it by this equation. So it's actually rate of change of voltage of your capacitor. And we are using periodic steady state. So in periodic steady state, you know that the value between in every period, so let's say I have a triangular waveform, and as you can see that every period, so every t, the value remains the same. So this is what we have used here. So the ultimate summary of this periodic steady state, yeah, anyone? Yeah. So the ultimate summary of our capacitor operating in periodic steady state is that the average of current through a capacitor is equal to 0. Okay. And similarly, for inductor, it would be the average of voltage across an inductor operating in periodic steady state is 0. So just keep it in mind, current through capacitor, average current through capacitor is 0 and average voltage through inductor is 0. So since this notion that we have developed of average current, average voltage, it's also applicable in the KVL and KCL form also. So when you have a loop, you can apply the same formula. Okay. Now, before understanding the operation of DC-DC back converter, you have to understand two things. In capacitors, capacitor is actually a constant voltage source. So an ideal capacitor with infinite capacitance acts as a constant voltage source. That the capacitor cannot be connected in parallel with a voltage source or a switch. Otherwise, KVL would be violated. Okay. So that's why initially, although we added capacitor, but we saw the limitation of adding capacitor. It will burn the switch. Why? Because you cannot just connect a voltage source or a switch in series with the capacitor. Same thing goes with the inductor. You cannot just connect an inductor in series with a switch. And this will cause your switch to be burned. Okay. Now, this is the circuit diagram of a back converter. So if you assume that your large capacitor, so your capacitor is very large capacitor, because you know capacitor will do charging, discharging, charging, discharging, charging, discharging. Now if your capacitor value is very large, so the ripple will also be minimal. Charging, discharging, charging, discharging, charging, discharging, something like that. Okay. So since V out has very low ripple, then assume I out, the current also has very low ripple. So what do we learn from the inductor voltage and capacitor current in the average sense is that the inductor current is this, capacitor voltage is this, but we know that the capacitor current, average of the capacitor current is 0 and the average of the inductor voltage is 0. Then we can actually apply this formula. Okay. When the switch is closed, this is the voltage across the inductor, which is V in minus V out. And similarly, this is the current IL minus I out. And we find this formula when the switch is on. Similarly, when the switch is off, we also find the condition of our load voltage. Then just by averaging the load VL, we obtain this formula. And you know that the average voltage across an inductor is equal to 0. And from this, we actually find the equation that the output voltage of our DC-DC back converter is actually D times the input voltage. So if your duty cycle is 0.5, so your output voltage would be half of the input voltage. If your duty cycle is 0.1, your output voltage would be 1/10 of your input voltage. And if your duty cycle is 0.75, then your output voltage would be 3/4 of your input voltage. Okay. So in DC-DC buck converter explanation, you have to add all these equations and things like that, and you have to explain. Okay. And as we know previously from the power balance equation, we can also find the output current. So since you can see, let's say we consider the case D equal 0.5. Okay. It means your output voltage is half of the input voltage. But here what is happening? 1 over 0.5 I in is equal to 2 times I in. So if you divide the voltage by 2, then your current will be increased by 2 times. Okay. Now here we have some waveforms of the capacitor of the load current. And as you can see, due to the capacitor charging, discharging, charging, discharging. Okay. And here we can find the ramp. Okay. So the rate of change of this line is actually given by this formula. P in minus B out by L. Similarly, here we have the formula when the switch is off minus P out by L. Okay. And from geometrical sense, we know that I average is actually the halfway between I max and I min. Now, what will happen? As you can see here, our current, is it constant or there is a ripple?
No, not constant.
Why?
Because the switch open and close, open and close.
Yes. So we have switch open and close, and not only that, we also have the capacitor and inductor. So they are charging and discharging. So that's why we will not have a constant value. But ripple, okay, so the delta I, we can actually control it. Okay. So how we can control it? This is the ripple delta I. The effect of raising and lowering I out while holding V in, V out, F and L constant. So let's say we just increase the output current. If you increase the output current, what will happen? And if you decrease the output current, what will happen is given here. And what is the summary? Is whether you increase or decrease the output current, it will have no impact on the ripple current. Okay. So this is something that you have to keep in mind, that if you want to control the ripple current, it's actually not related to the output current. And one thing you have to keep in mind, if you keep lowering the output current, then at some point, this will actually touch the zero value. Means your current through the inductor will be zero. It means at that time you have discontinuous conduction mode. And this is something that we want to avoid. Now, if you increase the switching frequency, so the faster you turn on or off your switch, let's say this is the baseline case. Now, if you increase the switch, what we can see? We can see that actually our ripple is decreasing. But if we decrease the switching frequency, means if we turn the switch on or off at a slower rate, then we can see that actually our ripple is increasing. So if you keep decreasing the switching frequency, at some point it may touch the zero value. It means you have discontinuous conduction mode, and which is something that we want to avoid. Okay. So lowering F actually increases delta I and moves the circuit towards discontinuous operation. So here you can see the effect of ripple if we increase or decrease the inductor value. So you see, if you increase the inductor value again, you can lower the ripple, but if you decrease the inductor value, then what will happen? Your ripple value will significantly increase. Now, if you keep decreasing the L, there will be some value which we mention as LC, the critical inductance, that will push your circuit to discontinuous conduction mode. Okay. So lowering L increases delta I and moves the circuit towards discontinuous operation. And by doing the formula calculation, you will be able to use a formula which is L onset equal V out times 1 minus D by 2 out times F. So this value of L will actually start the discontinuous conduction mode. Okay, and to calculate this, we have to consider the worst case duty cycle. Okay. There is also another alternative formula that uses the load resistor and sampling frequency. This we can use to solve a problem. So here, please be careful. Please carefully check how I solve this problem. So here in this question, what is asked? That a buck converter having a switching frequency of 10 kilohertz is to be operated with a duty cycle such that your duty cycle is between 0.5 and 1. The load is described by 25 ohm. Determine the value of the critical inductance so that the current is continuous. You see, up to this value, we are safe. Okay. Now, this is the formula. In this formula, we already know RL equal 25 ohm. Fs, sampling frequency is 10 kilohertz. Switching frequency, sorry. Do we know what is the value of D? Any idea, anyone, which value of D we should use?
Just take an average. Use
No.
0.75.
No, we have to actually take the worst case scenario, means the lowest value. Okay, so we have to take D equal 0.5. So in the exam, if you see this kind of question, always take the lowest value. Then by substituting these values, 1 minus 0.5, RL is 25 ohm divided by 2 times 10 kilohertz. You will find the value of your inductor. Any question about this math? No? Now we see another important, like in the, this is actually very important for the exam, that if I ask you to explain the impedance matching operation. So in the lecture, you may remember I talked about the impedance matching operation. So what is impedance matching operation is, we know that if we want to transfer the maximum power to our load, the impedance of my source and load should match. Okay. Now, in practice, let's say our load, this is constant. We cannot change it. Okay. So if we can put something in between that will artificially change the equivalent impedance of my output so that the input and output impedance matches, then I can ensure that my circuit is operating efficiently. Okay. So DC-DC buck converter is something that we can use as this artificial impedance altering method. So by controlling the switching of my DC-DC buck converter, I can actually change the impedance of my circuit. So here we see an equivalent representation. So what is the equivalent representation from the load side? What we see is actually load will see, a source will just see an equivalent load. Source will not see all these things. But if we can, by somehow artificially control this equivalent resistance, then we can ensure that the source and load impedance are the same, and this will ensure maximum power transfer. So actually we can find this R equivalent equal V in by I in, and from the buck converter formula we know that V output equal D times V in. So V in equal V out over D. And also we know I out equal I in over D. So I in is equal I out times D. Okay. So by substituting, we know that V by I is actually R. So your R equivalent is actually R load by D square. So if you control the D, you can actually change the equivalent resistance. So the buck converter makes the load resistance look larger to the source. So because you know this D is always less than 1. So if you take the square of something less than 1, it will actually reduce. Then 1 over that reduced value will actually give you a higher value. Okay. So here we are seeing one interesting application with solar PV, okay, photovoltaic panel. So what is happening here is like this is the open circuit voltage of your panel and this is the short circuit current and this is actually the power line. So the maximum power actually happens at 29 volt, okay, so something around here and at 4.5 ampere. If you do not operate your circuit at this point, it will not give you the maximum power. If you operate it here or there, you will actually not get the maximum power. So here you see the black line here, the black long line is for max power from the panels at this solar intensity level, attach R load equal this, because we know RL equal V out by I out. So we already know this is the out, this is this. So this should be the equivalent load resistance. So just by changing the duty cycle D, we can change the load resistance to make sure that it is 6.44 ohm. Okay. Now, as the sun condition is changing, means in the morning or in the noon time, the position of the sun, and in the afternoon, the position of the sun are not same. So when there is a change in the position, then your maximum power point will also change. You can also see it like kind of like equivalent resistor change. So this line actually represents 6.44 ohm. This line represents 2 ohm load resistor. And as you can see here, we get 55 watt. Okay. So to draw the maximum power, connect a buck converter between the panel and the load resistor and use D to modify the equivalent load resistance seen by the source, so that maximum power is transferred. So what we have to do, we have to just modify our duty cycle so that maximum power is transferred. That's why this kind of operation is also called maximum power point tracking. Okay. If you buy a solar panel, often they will say that this solar converter actually supports MPPT operation, means it can extract the maximum power. Okay. And this is actually the kind of like the circuit diagram for solar application. So this is actually the buck converter. Here you will connect your load. This could be a battery. Okay. And here you have the voltage panel. Okay. Ideally, we also add a capacitor. Okay. Because you know solar panels current is also not constant, so you will have ripple. You just add a capacitor to mitigate that. Okay. Okay. So that was the part about DC-DC buck converter. Now we are going to see another important aspect, which is the motor control. Okay. So motor control is important for the exam. You have to just understand the basic of motor control operation. So how a motor control actually operates, we have our supply, okay, which is the DC voltage. This could be the battery and things like that. Then we have a motor and in between we have inverter. So we actually control the inverter to control the motor, and we operate the motor in VFD mode. Okay, so it's variable frequency drive. So just by controlling the frequency of our excitation voltage, we can control the speed of our motor. And here you can see the basic idea. So we have a three-phase inverter. That inverter is connected to a DC voltage source, and that inverter actually controls the motor's output. Okay, and how we control the inverter? We actually compare our inverter, so the reference voltage with a carrier signal, and that carrier signal will actually give us the PWM. So when to turn on or off the switch. And here you can see the basic operation of sinusoidal PWM or SPWM. Okay, and as you can see in the SPWM, what happens that slowly, progressively, the pulse width actually increases and it gets maximum at the middle, and then again progressively decreasing pulse width. So this is the characteristics of sinusoidal PWM. Okay. Now, one thing you have to keep in mind that motor control is happening in a three-phase system. These three-phase systems, they are actually sinusoidal. Okay, so these are constantly changing. It is difficult to control signals that are continuously changing. So what we do, we introduce some sort of mathematical transformation to convert your sinusoidal signals. So this is the three-phase signal to two DC quantities. Okay, so this IQ and ID, they are actually DC, they are constant. Okay, so this mathematical transformation is actually very important in motor control. So going from here to here, it's actually this one is called the Park transformation, and here you have Clarke transformation. Okay, so what Clarke transformation does, it converts your three-phase signal into two-phase signal, and your Park transformation will do what? Two-phase signal into a two-phase AC signal to two-phase DC signals. So here I have presented the equations for our Clarke and Park transformation. So if you apply these formulas, you will be able to get the voltages and currents. So here this is the formula to obtain the inverse Clarke. So what is inverse Clarke? If you are given the Clarke transformation voltage, how you can go to the ABC? That's actually inverse Clarke. Okay. Sorry. And here, what we have, if you are given the DC and you want to get the AC, you have to apply inverse Park transformation. Okay. And if you are given the AC, you want to go to DC, you have to apply Park transformation. So these are all just.
Can you go through those equations for us, please? Instead of just skipping over them, if that's all right.
No problem.
Cheers.
So these equations are actually what? So you have three-phase signals, isn't it? And these signals are actually 120 degree apart. So let's say this is the base signal IA. Then the other signal would be positive 120 degree and negative 120 degree. So this is the negative 120 degree because 2 pi by 3 is actually 120 degree. Okay. And another would be positive 120 degree. So if you apply this formula, okay, so IA minus half IB minus half IC, and you multiply it by this constant, you will actually get I cos omega t plus phi, which is the theta. And here you have I beta. If you take this simple algebraic sum, you will get I sine omega t plus phi. Okay. In MATLAB Simulink, you already have this kind of block available. Clarke transformation, Park transformation. You just feed it with IABC or I alpha beta and things like that. Okay. So this is actually the derivation. So you can substitute the values and expand it using trigonometric formulas, and you will get these equations. So same thing here. Let's say I am given IA, IB. So sorry, I alpha, I beta. How I can go back to the IABC? It's actually we just apply this formula. So if we apply this formula, we will get it. Same thing here. Let's say we are given the alpha beta. So the Clarke transformed voltages, how we can get Park transformation is IA times cos theta, IB times sin theta. IB times cos theta, IA times sin theta. Okay. So if you apply this, you get a DC quantity, which is I at 0, 0. You see, what is, just for your information, what is I alpha? I alpha is actually I cos theta. This is theta. Okay. Then I'm multiplying it with cos theta. Plus I beta. What is I beta? I sin theta. Okay. Sorry. I sine theta. I'm multiplying it with sine theta. Okay. So if I take I as a common term, here I have cos theta times cos theta is cos square theta. And sine theta times sine theta is sine square theta. Okay. We know that cos square theta plus sine square theta equal 1. So we get this. And here what we get, what is IB? IB is I sine theta times cos theta minus what is IA? I cos theta. And what is sine theta? It's here. Equal to 0. Okay. So that's how we get this. And similarly, if we have the D and Q, we just apply this inverse Park transformation formula and we get to alpha and beta. So this is the overall block diagram. So in this block diagram, as you can see, this is actually the Park transformation. Okay. And here you have the inverse because you are given DQ, you will get ABC. This is actually the inverse Park transformation. Okay. Now, you may ask the question that we are directly using Park transformation and inverse Park transformation. So why we need Clarke transformation? This question may come to your mind. Okay. In fact, in practice, Park transformation does not happen automatically by using this formula. So always we convert our ABC to alpha beta. This is the Clarke transformation. Okay. Clarke transformation. And then from that alpha beta, we go to DQ. Okay. So if I show you the first block diagram, so this is how it actually happens. First, you convert 3-phase to 2-phase AC and then 2-phase to 2-phase AC to 2-phase DC. Okay, so ABC to DQ actually happens like this. So the block you have seen, ABC to DQ, here, okay, ABC to DQ, is actually this block. Okay, so if in the exam you see their question like, what is the importance of Park transformation and Clarke transformation in motor control? You can provide this kind of block diagram and explain that, okay, our signals are in 3-phase, they are AC signals. So Park transformation and Clarke transformation, they actually helps us to convert the AC signal into DC signal. Then you can provide the relevant equations. So that's actually another question covered. So now the last question. Okay. So the last question is actually about oscillators. So what is an oscillator? An oscillator is a circuit that produces a periodic waveform on its output with only the DC supply voltage as an input. It means if you just give a DC supply voltage as the input, okay, let's say V in, I give for example 5 volt. Okay. If you give the DC supply voltage as the input, you will get periodic signals like this. So this one is a pulse wave, this one is a triangular wave, this one is a sinusoidal signal, and things like that. So the output voltage of our oscillator can be either sinusoidal or non-sinusoidal, and depending on the type of the oscillator. So in this module, we concentrated mainly on the sinusoidal oscillator. So oscillators can also be classified into feedback oscillator and relaxation oscillator. We are only interested in the feedback oscillator. Because feedback oscillator is more easier to control. But things like, if I'm not wrong, things like crystal and things like that, they are more relaxation oscillator can be made using crystals and things like that. So the basic idea of oscillator is actually called positive feedback. So we all know that how our control system works. Our control system works like you compare your reference with your actual. Means you are taking actually negative feedback. So your actual value, you are taking the negative of it. In the case of oscillator, you actually do the opposite. You take the positive of it. Okay. So you use the feedback circuit using positive feedback. So positive feedback is characterized by the condition wherein a portion of the output voltage of an amplifier is feedback to the input with no net phase shift. Means if your original phase is 0 degree, your feedback phase will also be 0 degree. Means if you introduce any phase shift in the circuit, then it will no longer be positive feedback. Okay. So that's the thing. Ultimately, what will happen if your net feedback is 0 degree and you feedback a portion of your output into your input, then you can have oscillator. Okay. To make an oscillator, you need to ensure two conditions. The first condition is the phase shift around the feedback circuit should be effectively equal to 0. Means you cannot introduce any phase shift. If you introduce phase shift, then your oscillation will actually decay. And finally, the voltage gain around the closed loop feedback gain must be equal to 1. So you cannot introduce any voltage gain. If you introduce voltage gain, what will happen? Your circuit will become unstable. Okay. If you introduce voltage gain greater than 1, then your circuit will become unstable. And if you introduce voltage gain less than 1, then your oscillation will decay to 0. Now, one thing you have to keep in mind, oscillatory circuit initially starts from 0. Then it slowly increases and reaches the steady state value. So in the initial stage, you actually need to ensure that your closed loop gain is actually greater than 1. Okay. If the initial value is 0 and you increase the gain of 1, what will happen? Ultimately, it will become 0. So in this stage, in the transient stage, you need to ensure your closed loop gain greater than 1. And once you reach the steady state, your gain will become equal to 1. So for the oscillation to begin, the voltage gain around the positive feedback loop must be greater than 1 so that the amplitude of the output can build up to a desired level. And once you reach the desired level, then your closed loop gain should be reduced to 1 so that you have sustained oscillation. So to ensure that initially you have a positive feedback gain greater than 1, what people do is like initially a small positive feedback voltage develop from thermally produced broadband noise in the resistor, okay, or other components, or from power supply turn on transient, or later on I will show you there are some internal mechanism that operates only at the beginning. Once it stabilizes the voltage output, then that circuit will no longer operate. Okay. So there are different types of oscillator. You have RC feedback oscillator, LC feedback oscillator, and things like that. So in the exam, both RC type feedback oscillator and LC type feedback oscillator are important. So one important class of RC feedback oscillator is the Wien bridge oscillator. So this type of oscillator, they are actually suitable for frequency up to 1 megahertz. Beyond that, it is preferable to use LC type oscillator. So Wien bridge is by far the most widely used type of RC feedback oscillator. And as you can see here, this is actually the feedback configuration. So if you select R1 equal R2 and XC1 equal XC2, then you see that your output by input is 1/3. And here your resonance frequency is obtained by this formula. Okay. So this is actually the frequency diagram. So this is the resonance frequency. That's where you see you have the maximum amplitude. Okay. So this is one example of a Wien bridge oscillator. This one, what you have seen is the basic, and this is the Wien bridge oscillator. What is happening here? Here you have an amplifier. Okay. This op amp. And in the amplifier, you actually use a lead-lag circuit to provide the phase shift. And here you have the voltage divider rule, voltage divider to provide the necessary feedback. Okay. And as you can see that the gain of my circuit ACL is R1 plus R2 by R2. Okay. Now you have to ensure that overall gain is equal to 1. So if ACL is 3, here you have to have a feedback loop gain of 1/3. So 3 times 1/3 is equal 1. By doing this, you ensure that you have a stable output voltage. Now, initially, how can we introduce this condition, the closed loop gain greater than 3? This closed loop gain means overall gain, okay, greater than 1. To ensure that, you put a variable resistor and you just manipulate it at the beginning to ensure that your closed loop gain is greater than 1, the overall gain greater than 1 and closed loop gain greater than 3. And this will cause the oscillation to build up, okay. And once you reach to the stable value, then you return back to the nominal value. Now, this kind of configuration is actually not very useful, because if you design a circuit, you cannot ask your user, please, whenever you turn on your device, manipulate this. So you need to have some sort of built-in mechanism that can ensure that you have this kind of variable resistor at the beginning. So this is actually called the self-starting Wien bridge oscillator. This self-starting Wien bridge oscillator is actually uses some sort of automatic gain control mechanism. So when you apply the DC power at the first time, both Zener diode, this Zener diode, you see, this Zener diode, if you apply, this will be turned off. Okay. Once the Zener diode is turned off, then what will happen? The equivalent resistance is R1 plus R3. And then you can find the value here using this formula. Now, once the voltage reaches the steady state value, then what will happen? This Zener diode will start to conduct. Once the Zener diode will start to conduct, this path is on. This is a short circuit then. So when you parallel a short circuit with a resistor, what will be the value of resistor? It will also become 0. Okay. So when you reach the steady state, this R3 will become 0. So 0 by R2 is 0. And 3 plus 0 equal 3. So initially your ACL is greater than 3 or your overall gain greater than 1. But once you reach the steady state value, your gain will become 1 or ACL equal 3. Now there is one limitation. The Zener feedback is simple. However, it suffers from non-linearity of the Zener diode that occurs in order to control the gain, because Zener diode is not a linear device. At the beginning of today's lecture, I showed you Zener diode is not a linear device. Its curve is something like this. Okay, so it's a non-linear device. In the past, okay, in some older designs, a tungsten lamp was used in the feedback circuit to achieve stability. Okay, so a tungsten lamp was used to provide that initial self-starting capability, but you know, tungsten lamp, they do not have long life and they have some limitation. So you can also use this kind of edge effect or junction field effect transistor, okay, to provide that initial startup condition. Okay, so it's ultimately controlling the R3. If you can control the R3, then you can ensure that your oscillator will self-start. So if I ask you in the exam this question, that explain the self-starting operation of Wien bridge oscillator, would it be too difficult for you?
Yes.
Well, the answer is here. Okay. So the last thing that I want to show you is the Colpitts oscillator. So far we have seen RC oscillator.
Sir, can I just see that last slide, please?
Yeah.
Thank you.
Well, these are also self-starting mechanism. So this is also self-starting mechanism of Wien bridge oscillator.
There you go, I've seen it now. Thank you.
Now, the Colpitts oscillator. So in the RC oscillator, you use RC feedback. and this type of oscillator are suitable for frequency up to 1 megahertz. In the Colpitts oscillator, we use LC feedback. Okay, so inductor and capacitor, and this LC feedback is actually suitable when you want to go for higher oscillation frequency. So LC feedback elements are normally used in oscillator that require higher frequency of oscillation. Another advantage of Colpitts oscillator is we do not need to use op-amp. Okay, in the RC oscillator we used op-amp. Okay, but op-amp has some frequency limitation. So because the frequency limitation, lower unity gain frequency of most op-amps, discrete transistor like BJT and FET, they are more suitable as the gain element in LC oscillator. So Colpitts oscillator uses an LC circuit in the feedback loop to provide the necessary phase shift and to act as a resonant filter that passes only the desired frequency of oscillation. Okay. So the resonance frequency of your Colpitts oscillator is given by this formula, where CT is this. This oscillator is also your coursework question, isn't it?
Yeah.
It is.
Yeah.
It is part of it.
Yes. So I guess you already have good idea of Colpitts oscillator. So if you see a question in the exam, explain the operation of Colpitts oscillator, I hope you all will be able to answer it appropriately. So as we have seen previously that we need oscillation to start. And in the oscillation startup, our overall gain should be greater than 1. So the attenuation of the tank circuit is the output of the tank VF. So this VF is actually the feedback voltage that you pass to your oscillator. Now, if you want to make sure that your overall gain is greater than 1, this AV must be greater than C1 by C2. So here you can see some formulas that ensure that your AV is greater than C1 by C2. But due to this tank circuit operation, it will initially increase, but after a while, when the value is settled down, then your overall gain will be less than 1. Okay. So here are some operations that is explained that Zin is the amplifier load that feedback circuit and lower its Q, thus lowering the resonant frequency. So to minimize the effect of BJT, we can also use a FET, so field effect transistor that has, how to say, lower input impedance. So lower input impedance means ultimately it will not change the resonance frequency of our circuit. So in the exam, you are already trying, in the coursework, you are trying BJT. So one advice, you may also consider to use a FET, field effect transistor, and show the comparison that, okay, by using a field effect transistor, maybe we get a better result. Okay. So this may give you some extra points. Okay. So unlike other oscillator, this oscillator also got some, some tricks that engineers use to ensure it is starting up appropriately. So here there is one configuration. So here a load capacitively coupled to oscillator. Okay. So you put a capacitive coupling, and this capacitive coupling can actually reduce the circuit Q or quality factor. Some people also come up with the idea of using transformer coupling, okay, to reduce the effect of impedance by using impedance transformation. So you can use the transformer to modify the impedance. Okay. So this is the last part of today's lecture, the revision lecture. So here we have a simple math. Now we need to find the operating frequency of this circuit. Okay. So for Colpitts oscillator, we know that the resonance frequency is 1 over 2 pi square root of LCT, isn't it? This part. Now in this circuit, capacitors are actually in series. So CT, we already know the formula. What is CT? C1 C2 by C1 plus C2. What is C1? 0.001 microfarad times 0.01 microfarad. So after simplification, we find it as 909 times 10 to the power minus 12 farad. Okay. We already know the value of inductor, which is 15 microhenry. So our resonance frequency will be 1 divided by 2 pi, okay, square root of L. L is 15 microhenry times CT is 909 times 10 to the power minus 12. Okay, and the answer is actually 1361 kilohertz, means 1.361 megahertz. Okay, so we found the operating frequency. Some of you asked this question in the Teams chat box to discuss about the parameter selection. Are you looking for something like this or something else?
Do you have to calculate the values of the other components as well, or is it just the tank circuit?
No, the tank circuit is one. The other circuit also, the other circuits you see, they are mostly, how to say, by trial and error. Okay. So you need to find some reasonable value and you have to justify.
What? So, like, could you use another circuit that you've seen somewhere and use that as a like a reference point to start with? Or?
Yeah, you can use that, and you can see that why I am using, like, let's say you use R1 equal 1 kilo ohm. Then you can how to say, you need to just explain that why you selected 1 kilo ohm. You can see that in a reference, I don't know, you just cite in why. Okay. A similar configuration is used, and what are the advantages of using this configuration and things like that. Okay. So it's not just I saw it in that paper, I am using it. So you need to give a bit more justification.
Okay, thanks. So find something similar and then reference it and justify it.
Yeah. So you know the thing is, for this kind of for the tank circuit, it is easy to find formula. But for all these other, you do not have any explicit formula. So these are more like design knowledge. Okay. And people, whenever they come up with this kind of design, they give some sort of justification that why they are actually using this value. It's not just some random values.
Okay, but we don't have to actually calculate them ourselves and derive them.
Yeah. So if you calculate, of course, you get more points.
How do you do that?
Yeah, but well, then you have to use those justification from the literature that in paper why they use this formula. So we are considering this formula. You got the point?
Yes, that's referencing them, but you don't have to calculate them yourselves.
Yes. So if you just use their value, you will get relatively less mark. If you use your own value and using their justification, you will get more mark.
Okay. So yeah.
Okay. So in my opinion, better to do something rather than doing nothing. Okay. So we already got the resonance frequency. So this is actually the operating frequency of our circuit. So this oscillator will oscillate at 1.361 megahertz. Now another question that you have to do is the feedback fraction. So this feedback fraction, look, here we have a feedback fraction, and that feedback fraction is actually given by the formula. So what is C1? This is actually the feedback fraction. Now let's say for some reason I don't have this kind of capacitor. Okay. but I have two capacitors, so that MV equal 0.25. Can you now calculate the operating frequency of this circuit? Any idea, anyone, how we can solve this? So let's say we consider our MV equal like 0.2. Okay. So MV equal C1 by C2 equal 0.2, or C2, sorry, yeah, C1 equal 0.2 C2. So now let's say we select the value of this C1. Okay. So if for a given C1, what would be the value of C2? Okay. So what is this? Let me check. 0.2 times 0.6.
Excuse me, can you just solve the problem that you've put on the board? Because now you've made it like kind of a bit confusing for me. Because I wanted us to just solve the problem that you've put.
Yeah.
So this is a feedback fraction.
Yeah. Now the new question is, let's say I'm giving you the feedback fraction.
All right.
Okay. So let's say, for example, now the feedback fraction, for example, for a given feedback fraction of 0.2, determine, okay, for a given feedback fraction, find the operating frequency. Okay. Okay. So let's say my feedback fraction is 0.2. So from this formula, I can find C1 equal 0.2 C2. Let's assume, since you are not given the value, let's assume that my capacitor C1 is this. Okay. You can assume whatever values you like. Okay. So this would mean C2 is 0.0002 microfarad. Okay. Now, once we know our C2, then we can find the CT. Okay. And once we know our CT, we know our resonance frequency, which would be equal to 1 over 2 pi square root of L times CT. This L is 15 microhenry, and CT will come from this equation. So what is C1? C1 is 0.001 microfarad. And what is C2? 0.0002 microfarad. Okay. So this will help you to solve this problem. Any question about the last part?
So what does MP stand for?
Which one?
MP.
MP, sorry, it's this one. This is the feedback fraction.
Yeah, is that MV or is that MP?
It's MV. Okay.
Oh, MV.
Yeah.
And also, do you know when you put C2 equals 0.2 times 0.01?
Yes.
Where did you get that formula from?
Just check here. What is C1?
Check. It says C1 is MV times C2.
Yeah, so 0.2 times C2. From this formula, I got this. And this is 0.2. And what is my, sorry.
Isn't it meant to be divided?
Yeah, it should be C2, not C1. Okay.
Yeah.
It's up to you. I can either you select C1 then find C2, or you select C2 find C1.
Oh yeah.
So in this case, it would be slightly changed. Sorry for the. Okay. This one would be.
So MV means feedback fraction, yeah?
Yeah, MV means feedback fraction.
Okay. Thank you.
Okay. No problem. So yeah, you just apply the formula, then you get the operating frequency. That's it. So tomorrow would be the last part, and that last part would be about the high frequency modeling. So that would also be the how to say, kind of like revision of that part. Okay.
Is that going to be online as well?
Yes, this I'm going to, yeah, that's also going to be online. I'm going to upload it now, this slide. Okay.